Last time we talked about the capacitor, where it needed a changing voltage in order for a current to flow. So today we'll talk about the inductor. It's kind of opposite. Actually, we need a changing current in order for there to be a voltage drop across the inductor. And the reason for that is because the inductor is a coil. And so if you imagine we've got a current that flows, it's almost like if the analogy is that current is sort of like water that flows through a hose. So if you have water that's pushing on like a stationary water wheel, it's going to kind of resist the push of the water before it actually starts getting going. Sort of like a merry-go-round, it's hard to push it at first, but once it's going, you barely have to push it at all. And so it's really similar, actually, if we were to hook up an inductor to a DC source that's not changing. If it's just supplying a continuous current, this is going to spin quickly like a water wheel or a merry-go-round, where it's actually not going to have any voltage drop. It's just going to look like a wire. So hooking up an inductor to DC is going to act like just basically a short circuit. So given that we need a change in current in order to have a voltage drop across an inductor, our voltage equation is V as a function of T is the inductance value in henries. This is just an intrinsic constant to the inductor times the derivative of the current with respect to time. Okay, so d I of t dt. And then to get the current, we have to get this term by itself. So to solve for how much current flows through the inductor, I will do di dt here. I'm going to bring everything else on the other side of the equal sign. So I have just this by itself, and that's going to be 1 over L times V of t. And then to undo this d dt, I have to do the opposite of derivative, which is take the integral of both sides. Okay, so by the fundamental theorem of calculus, I have the integral and the derivative are basically going to cancel each other out, right? They undo each other. So I have I of t, so the current flowing through the inductor as a function of time will be given by 1 over L, if I pull this constant out of the integral, times the integral from some initial time to a final time. A lot of times this is going to be 0 and it goes to a particular time, like starting a stopwatch, of the voltage with respect to time, and we'll put tau in there as an integration constant, d tau, plus whatever initial current that's stored in the inductor. Okay, so these are our current and voltage equations for the inductor. And again, it looks different than Ohm's law, because Ohm's law, V equals IR, it's basically just a linear function, where these are not linear functions. This is a derivative function, and this has an integral term. Okay, so then just to continue with the review of inductors, if you have, the next thing we need to know is if we have multiple inductors that are in series, this is L1, L2, L3, then the L equivalent is just going to be the sum of these, L2 plus L3. Okay, so they combine in series just like resistors. And then if these are in parallel, these are going to combine just like resistors in parallel. 1 over L1 plus 1 over L2 plus 1 over L3 with this reciprocal relationship. Okay, great. So remember, for capacitors, it was the opposite. If you had capacitors in series, they added like inductors in parallel. And if you had capacitors in parallel, they added like inductors in series. But this is straightforward. This looks very familiar to us. It's the same way we would combine resistors. So let me know if you have any questions about this brief review of inductors, and then we can start talking about impedance.